Okay, so now let me give you the general formula which I appealed to in the previous video in calculating expected value of the two gambles. So here it is. So given an act A with two possible consequences, C1 and C2, we say the expected monetary value of A is the probability of C1 times the amount of money you gain in C1 plus the probability of C2 times the amount of money you gain in C2. So again, as I mentioned in the last video, you can think of this as giving you a weighted average of the monetary outcomes where the weights are the probabilities of those outcomes. So here's a couple things to note. Sometimes a game doesn't just win money. There can be outcomes of a game or a gamble in which you lose money or you don't gain anything at all, as we saw with the die game. So in those cases, we use negative values here for losses. Um, so if the outcome one, C1, say you lost $5, here you'd put negative $5 as this value. Okay. Another thing to note too is that strictly speaking, in this formula, we're considering the probability of each outcome given the action. So these probabilities are actually conditional probabilities. So we're considering the probability of consequence n given that you perform that action. So this, strictly speaking, should be probability of C1 given A, and here should be the probability of C2 given A. But I'm going to gloss over that for simplicity. So I want you to consider another example. So suppose the game in question is that the dealer is going to roll a fair die. So you'll win $3 if the die comes up 5 or 6. So far this is the same as the die game from the previous video. But if if the die does not come up 5 or 6, if it comes up 1 to 4, you're going to lose $1. Okay, so in the earlier die game, you lose nothing. You just get $0 if you get 1 to 4. But in this case, if the die doesn't land 1 to 4, you'll lose $1. You have to pay $1 to the casino. Okay, so let's ask, what is the expected value of this game? Another way of putting that is this game worth playing? Is it worth the chance of winning $3 if the die comes up 5 or 6 versus a chance of losing $1 otherwise? Is that worth playing? And we can use this formula here to tell us. So we apply it. So this is just a formula. So C1 is that the die comes up 5 or 6. So in that case, you get $3 here and 1/3 probability. And then C2 is it lands 1 to 4. In that case, you have minus $1 here and 2/3. So filling that in, and then it's doing a bit of math. What you realize is that here, the expected value of this game is 1/3 of $1, or 33 cents, or 33.33 repeating cents. So what this tells us is actually that this game is probably worth playing. So even though you have a chance of losing $1, you have a pretty high chance of gaining 3. So the expected value of this game is positive. So the next thing I want to mention is that we are going to consider gambles and actions which have more than just two possible consequences. And actually this formula can be, the idea behind this formula can be applied no matter how many possible outcomes there are of the action, so as long as each of the outcomes has a has a certain value, either positive or negative or 0, associated with it, and also so as long as these outcomes are weighted by probabilities. So given an act A with n possible consequences, where n may be however high you want, we can say that the expected monetary value of that action is what you get from summing up all the products of each of the outcomes times probability of that outcome. Okay, so here is a fancy math symbol which might intimidate some of you, but all this is saying is that you have this product here that is the probability of an outcome times the amount of its value. You have this thing here summed up enough times to cover all of these actions. Sorry, all of the outcomes of the action. Okay, so I'm going to work through an example right now, which shows you how this works. So here is another die game. So a fair die will be rolled, and you're going to win $1 if it's 1 or 2. So that's the first possible consequence. $2 if it's 3 or 4. Okay, but if it's 5 or 6, you're going to lose $3. So let's ask, what is the expected value of this game? And now here we have 3 possible consequences, so we can't apply these earlier formulas, because this earlier formula just tells us how to do it with 2 outcomes. But as I've stressed here, all we have to do is just add an additional outcome. So you just add an additional term summed up, which is probability of C3 times the amount of money of C3. And that's exactly how we applied this fancy formula here. So we simply just add another term that we're summing up. And so just as we look at the probability of the first outcome times the amount of money, and we add the probability of the second one times the amount of money, we just add again the probability of the third one times the amount of money. And for any other possible outcomes, we just add the amount of money that we win or lose in that outcome weighted by its probability. And so here we just simply fill in the details that are given to us by the example. So there's a 1/3 chance of winning $1, there's a 1/3 chance of winning $2, and there's a 1/3 chance of losing $3. And when we calculate this, we get 0. So really the expected value of this game is 0. So what that tells us is that we have nothing really to gain from playing it. Okay, there's a higher chance of winning something. Okay, either $1 or $2, but the amount of money you lose if it lands 5 or 6 kind of fully outweighs those 2 possibilities. So you really should be kind of impartial or unbiased about this game. So whether you play it or not shouldn't matter. Now, again, and also as was mentioned in the reading from last week, we can't ultimately identify the exact amount of money won or lost with the amount of utility. Okay, so overall, we have to consider more than just the amount of money won or lost in a gamble or an action. Okay, but that is an important complication that we're going to talk about on Wednesday. But the point now is that we can perform very simple calculations of expected monetary value by just sticking in the amount of money here. And we're going to see on Wednesday how we can replace that amount of money with something more general, which is called utility. And the point I'm trying to make now is that often the utility of an amount of money is not just identical to that amount of money. And so again, that's a point we will come back to. But right now, in this lecture, I really want to focus on showing you how to perform these simple calculations of expected monetary value. So now, and we have worked through several examples, and I've given you the general formula, which you will apply to these examples. And I will now conclude the lecture with a little tip. So all of these gambles we've looked at so far, we don't assume that it costs anything to play them, okay? But often it does cost something to gamble. So for instance, you have to buy a ticket to a lottery, or you have to buy chips to play at the casino, etc. Okay, and I should also say that in order to show you the notion of expected value, I'm talking about the notion of expected monetary value. And the very simple way of explaining or applying the notion of expected monetary value is with gambles. And so I'm not here trying to endorse gambling in any sense. I think gambling can be very dangerous and addictive, but the point of mentioning all these gambles right now is just to give you a simple kind of simple environment to perform these mathematical calculations where we have just simple amounts of money and we just calculate the expected value based on the money. Okay, but in any case, here is a final quick tip. So suppose that a game costs, sorry. So suppose that a game costs some money to play. How do we then incorporate that cost of the game into the calculation of the game's expected value? And here is the simplest way. You can think of the cost as an additional outcome where that outcome has a probability 1 or 100% probability of losing that amount of money, which is a cost. Okay, so let me try to make this more concrete. So suppose, for instance, the die game just mentioned here costs $1 to play. So we can then ask, should you do it? Should you play this game? So here we have the exact same terms as before, the three outcomes. So this C1 is that the die lands 1 or 2. C2 is that it lands 3 or 4. And C3 is that it lands 5 or 6. Okay, so these are the three outcomes. But in the case where we're assuming this gamble will cost $1 to play, what we do is we add another outcome. And this outcome is kind of trivial in the sense that there's a 100% chance that it will happen. And it's a 100% chance that you'll lose $1. And that's because you're paying $1 to play it. So to incorporate the cost of a game or a gamble into the expected monetary value calculation, you just simply add another term to what you're summing up, where you have where there's a 100% probability, or probability 1, which is the same thing, of losing the amount of money which is the cost of the game. So, and the 1 times anything is just that thing. Okay, so here we simply have the same numbers as before, but where we basically subtract $1. Okay, and when we do that, we see that the overall expected value is negative $1. So in this case, actually, it doesn't make sense to pay any money to play this game. And that makes sense because we said here, because the game where we didn't pay anything, the expected value was 0. So we shouldn't really expect to gain or lose anything. And therefore, since the expected value of this game without a cost is 0, it doesn't really make sense for us to pay any money whatsoever to play it. And so when we pay any money whatsoever, the expected value will be go down by that amount of money that it costs. And so what we see is that this game, doesn't make sense to pay $1 for. And we showed that by incorporating the cost as an additional outcome, which had 100% certainty.